Hello learners, welcome to the next session. In the previous session, we have already discussed about VBT or valence bond theory. Okay, and in valence bond theory, we have said that the nature of bond between metal and ligand, it is covalent in nature, right? And today in the session, we are going to start with the next theory, that is crystal field theory. And in crystal field theory, we are taking the nature of bond between the metal and ligands as ionic. Okay, we are taking the bond as ionic between that of the metal and ligands. So what is the thing with what crystal field theory? What are the postulates related to each and everything we will discuss in the session. So as you already know, valence bond theory, it took 3 sessions to complete, right? We have discussed a lot of examples related with valence bond theory, and it took 3 parts for completion of valence bond theory. Similarly, here crystal field theory, we have a lot to discuss in this topic too. So it will be in a lot of parts. Okay, so this is crystal field theory part 1. Okay, so without any further delay, let us start. First of all, here we are going to discuss some of the postulates related with crystal field theory. Okay, so first of all, I have already said you the type of bond or the nature of bond between the metal and the ligand is considered as ionic in the case of crystal field theory. Okay, so let us start with the first postulate. What is it? It assumes the metal-ligand bond to be ionic, arising purely from electrostatic interactions between the metal ion and the ligand. Actually, what is an ionic bond? If we take a metal A and a non-metal B, as we know, metals have the tendency to lose electrons, thereby forming a positive ion which can be called as cation, whereas non-metals have the tendency to gain electron, thereby forming the negative ion or the anion. As we know, opposite charges attract with each other and there forms a very strong force of attraction between these two ions, and which results in the formation of an ionic bond. Okay, they will exist as a they will exist like a complex. Okay, so they will exist like this. There will be a strong electrostatic force of attraction between these opposite ions. This is how ionic bonds are formed. So in crystal field theory, it assumes that the bond between metal and ligand or the metal ligand bond, it is ionic. Okay, which arises purely from the electrostatic interactions between the metal ion and the ligand. There is strong electrostatic forces or interactions between the metal and ligand. Okay, this is what assumed by the crystal field theory. Okay, so here as you can see, there is a metal and a ligand, and there forms which type of bond is formed between the metal and the ligand? There comes the ionic bond, that is due to electrostatic attraction, there forms a coordinate complex. That is what said or assumed by the crystal field theory. Clear? Is it clear to you? Now, moving on to the next postulate, that is ligands are treated as point charges in case of anions or point dipoles in case of neutral molecules. So what does it postulate says here? It is saying that we can classify or ligands. There are 2 types of ligand. The first one is negative point charge ligand. Okay, negative point charge ligand. As we know, some of the ligands, they are anionic in nature. They are carrying a negative charge, right? So those are the first type of ligands. And here comes the second type, that is point dipole. That means in some of the cases, if we are taking water as a ligand, water, what is the charge? It is a neutral molecule, right? If we are taking water, it is a neutral molecule. So what happens here? Here, in the case of water, this is how water is. Okay, a single oxygen and there will be 2 hydrogen. If we are comparing the electronegativity of oxygen and hydrogen, which one is more electronegative in nature? Which one? It is oxygen more electronegative when compared with hydrogen, right? So here oxygen being more negative pull the electron pairs shared between oxygen and hydrogen towards itself. More electronegative means it has a tendency to pull the electron towards itself. So here there arises a slight negative charge for oxygen, and here electrons are moving away from hydrogen, therefore there arises a very small positive charge, and this is what a dipole is, right? This is what a dipole is, and if water is the ligand, this negative, this oxygen with a slight negative charge will reach the metal. Okay, the oxygen reaches to the metal, towards the metal. This is how the second type of ligand, that is, can be called as point dipole. Here, as you can see, if this is oxygen and these are the hydrogen, there is a small negative charge on the oxygen atom in the case of water. Okay, so it will move through, or the ligand will approach through the oxygen atom which is carrying a negative charge. So ligands, they are of two types. What are they? Negative point charge, okay, and it is point dipole. And metal is considered as what? It is considered as point positive charge. As we know, metal is considered as point positive charge. Okay, so this is the second postulate that we are discussing, that is, ligands are treated as point charges in case of anions, or point dipoles in case of neutral molecules. What is it? Ligands are treated as either as point charges in case of anions, and if it is neutral molecules, we are considering it as point dipole. Okay, here the metal is considered as a positive point charge. Is it clear to you? Is it clear to you? Okay, fine. Now moving on to the next postulate. What is it? The 5 d orbitals in an isolated gaseous metal atom or ion have same energy, that is, they are degenerate. Okay, what does it mean? Here, if we are taking the free metal ion or atom, here you can see if this is the free metal atom or if this is the free metal ion. Okay, this metal ion is having vacant d orbitals, right? Then what about these d orbitals? All the d orbitals are of same energy. Okay, these d orbitals are having same energy, or we can call it as degenerate. What is the word? It is known as degenerate. Degenerate means they are having the same energy. All the 5 orbitals that are, what are the 5 orbitals here? It is dxy, dyz, dxz, dx square minus y square, and dz square. Okay, all of them are having the same energy, or they can be said to be degenerate. Okay, so this is what the case with the metal ion or the metal atom. All the d orbitals, they are degenerate. Okay, and this degeneracy is maintained if a spherically symmetrical field of negative charges surrounds the metal atom or ion. Okay, so first of all, it was the metal atom or the metal ion itself alone in a field. Okay, it was alone. After some times, the ligands starts approaching it from far away. Okay, the ligands are approaching the metal far away. Okay, please imagine the situation. This is just an imaginary situation. Okay, imagine the situation. The metal ion or the metal atom, it is alone in there, and the ligands start approaching it far away. Okay, and the ligands are approaching it in a symmetrical way. In a symmetrically spherical way, the ligands are attaching the metal. Okay, so what happens? Okay, the degeneracy, does it will be affected? Of course, no is the answer. Okay, the degeneracy will not be affected if the ligands are approaching the metal in a spherically symmetrical way. As you can see, here is the symmetrical field of ligands. As you can see, the ligands are approaching our metal ion or our metal atom here in a very symmetrical way. Okay, so this is the symmetrical field of ligands. Then what happens here? If the ligands are approaching the metal in a symmetrical way, or if it is approaching symmetrically, then there will be the same degenerate orbitals. There will be no change in the energy between this d orbitals. The degenerate orbitals will be the same, but actually the energy of all the d orbitals is raised to a little bit. Okay, the energy of all the 5 orbitals, okay, after they approach from the ligands symmetrically, all the 5 d orbitals, okay, there occurs an equal energy increase for all these 5 orbitals, and here we will get the degenerate orbitals itself with a particular high amount of energy. This is what we will get. Okay, I hope you understood it clearly. So the next postulate of crystal field theory is the 5 d orbitals in an isolated gaseous metal atom or ion, they have the same energy. That is, they can be said to be degenerate. Okay, and this degeneracy is maintained. Okay, all those 5 d orbitals will have the same energy if a spherically symmetrical field of negative charges surround the metal atom or ion. Okay, all of them, if we are taking all the 5 orbitals, they have the similar energy. But when they are compared with the first energy, okay, if this is the second case and if this is the first case, okay, when compared with the first case, there is a little increase in the energy. But if we are taking the energy of the 5 d orbitals, between these 5 d orbitals, it is the same. There is no change in the degeneracy. So, on the approach of the symmetrical field of ligands, the degenerate orbitals are them, but also the energy of all the d orbitals is raised. All the d orbitals, the energy raised simultaneously. Is it clear to you? This is the third postulate. Clear? Okay. Now, moving on, the next one, that is when the ligand approaches the metal, here we can say or we can conclude there is electrostatic attraction due to positive and negative charges occurring in there. Similarly, there will be the electrostatic repulsion due to electron present in metal and ligand. Is it so? Here in the d orbital of the metals, okay, if the metal is having the d orbital, this is a d orbital, right? If an electron is present in the d orbital and if the ligand is having a negative charge, okay, then there will be a repulsion between this negative charge and the electron present in the metal, right? So, electrostatic, there occurs a electrostatic repulsion due to electron present in metal and ligand. Similarly, there will be an electrostatic attraction due to positive and the negative charge. Okay, if we are taking the metal as a whole, it is positive charge, and the ligand, if it is negative, of course there will be a electrostatic force of attraction between the metal and the ligand. Similarly, the electrons in the metal and the ligand, okay, there will occur say electrostatic repulsion. Okay, so due to ligand field, energy of the d orbitals is increased. When the ligands are approaching, there occurs both electrostatic attraction and electrostatic repulsion. And here, when the ligands are approaching the metal in a symmetrically spherical way, what happens? The energy of the d orbitals is increased. Okay, due to ligand field, the energy of the d orbital is increased. So, first of all, we have said that, okay, the bond between the metal and the ligand is ionic in nature, or we can say there is electrostatic attraction or interaction between the ligand and the metal. Okay, in the second postulate, we have said that there is electrostatic repulsion due to electron present in metal and the ligand. And as we concluded that due to the ligand field approaching or due to the ligands approaching our metal, what happens? All the energy of all the d orbital increases, or the energy of d orbitals is increased. Is it clear to you? Okay. Now, before the next postulate, let us discuss the shapes of the d orbitals. As we know, d orbitals, there are 5 d orbitals. What are they? dxy, dxz and dyz. Let us discuss the 3 of them here, and we will discuss the rest of the 2 in the next slide. So here you can see the shapes of the d orbital. Okay, so if you can see, this is the x-axis, this is the y, and this is the z-axis. In this particular shape, you can see the lobes here lies in between the y and z axis, right? The d orbital lies in between the y axis and the z axis. Therefore, this is the shape of dyz. Is it clear? Now here the lobes are lying between x and z. The lobes lies between x and z. Therefore, the orbital is dxz. And here in the case, it is between, the orbital is between x and y. The lobes are lying between x and y. Therefore, it is dxy. So, in the case of dxz, dyz and dxy. Okay, dxz, dxy and dyz. In all these three orbitals, what happens? The d orbitals are lying in between the axis. In between the axis, right? Therefore, all these three d orbitals are between the three axes. Therefore, we can call them as non-axial orbitals. What are they called as? Non-axial orbitals because they are lying in between the axis. Okay, so dxy, dyz and dxz. Is it clear? Now, the remaining two orbitals, what are they? Dx square minus y square and dz square. So, here comes the shape of dx square minus y square and dz square. In these two orbitals, you can see the lobes are lying along the axis. Okay, they are lying along the axis. So, this is the shape of dx square minus y square. Okay, here the lobes are lying in the x-axis and in the y-axis. So, this is dx square minus y square and here it is dz square. Okay, z square, the lobe lies along the z-axis and there is a ring around the lobe. Okay, a donut shaped ring around the lobe. So, this is the shape of the dx square minus y square and dz square orbitals, and you can see these orbitals lies along the axis. Okay, these two orbitals are on the axis. Therefore, they can be called as axial orbitals. So, if we are taking the 5 d orbitals, 3 of them are non-axial orbitals, which are they? dxy, dxz and dyz. Then the remaining 2, they are axial what? Orbitals. They are dx square minus y square and dz square. This is the shape of the d orbital. I hope it is very clear to you, the shape, right? Now, without knowing the shape, we cannot understand the next postulate about crystal field theory. Okay, so I hope now the shapes about the d orbitals, it is very clear to you. Now, moving on to the next postulate, that is, in a complex, the negative field from ligands, anions or dipolar molecules like ammonia and water causes asymmetry, lifting the degeneracy of d orbitals and leading to their splitting. What does it mean? Here, as we have already said in the first postulate, the central metal atom or ion is there and the ligands start approaching it. Okay, the ligands are approaching it. Let me show you. If it is a octahedral complex, okay, all the ligands will approach the central metal atom or ion octahedrally. It is in an asymmetric way. Then, of course, the degenerate d orbitals will be affected. Okay, the degeneracy of the d orbitals will be affected if the ligands are approaching the central metal ion or atom in a asymmetric way, which will result in the splitting of the d orbitals. This is what the postulate is. Now, read it once again. In a complex, the negative field from ligands, that is anions or dipolar molecules like ammonia and water, causes asymmetry, lifting the degeneracy of d orbitals and leading to their splitting. Okay, as a result, what happens if the ligands are approaching asymmetrically? The degenerate orbitals. Okay, this was the degenerate d orbitals, 5 d orbitals. It will split into 2. Okay, it will split into 2. Here comes dx square minus y square and dz square. And then it will split into dxy, dxy, dxz and dyz. Here, the axial orbitals dx square minus y square and dz square, the axial orbitals are having the greater energy. Okay, we will discuss it in detail. Why these these 5d orbitals split like this. We will explain it very clearly. We need to study about the octahedral splitting in coordinate complexes. So in that particular portion, we will discuss it very clearly. Now it is the postulate of crystal field theory. Right? Now moving on, if we are taking the tetrahedral complex, similarly, if the ligands, the 4 ligands approaches our metal atom asymmetrically, the degeneracy of the d orbitals of our metal ion, it will be affected, resulting in the splitting. Okay, and in tetrahedral complexes, how is the splitting? Here you can see the non-axial orbitals are having higher energy when compared with the axial orbitals, that is dx square minus y square and dz square. Is it clear to you? So these are the postulates of crystal field theory. Once again, the postulates are, first of all, we have said that there is an ionic bond, electrostatic interaction between the metal and the ligand. Then we said that when the ligands start approaching the metal in a spherically symmetrical way, what happens? The degeneracy remains the same. Okay, all the d orbitals will have the same energy. Okay, then we have said that when the ligand approaches the metal in an asymmetrical way, the degeneracy of this d orbitals will be affected, resulting in the splitting of this d orbitals. And the splitting is in different ways according to the geometry of the ligands or the geometry of the complex. Okay, it will be different. The splitting of d orbitals will be different. Mainly we have to study about octahedral splitting and tetrahedral splitting in the case of coordination complexes, which we will discuss in the coming sessions. So part 1 of our crystal field theory is completed. I hope everything is very clear to you. From the next session, we will discuss in detail about the octahedral splitting in coordination complexes. Until then, study well, happy learning. Thank you.